Let's start our seminar, and first of all, I suggest to solve the following simple task, and to find the solution this linear system. We have the linear system from three equations and four unknowns. And in this case, easy to see that this linear system can has either infinitely many solutions, either has no solution. And we try to apply Gauss elimination method to solve this solution, and after them we try to express the solution by various way present in the various form if the system has solution. First step, to transform into zero the elements of first columns, and we have some evident first step. If we can transform this element into zero, we can apply the elementary operation of the third type and subtract from the second row first row, multiply onto, and on this place, if we can obtain the zero, we must subtract from these rows. First row multiply by 3, and we have the following operation. R2, we put the difference R2 plus minus to R1. R3 we put R3 plus minus 3R1. We rewrite the first row. And we transform second row. We multiply by minus 2 the corresponding elements of the first row and 2, and add to the second row. Minus 2 multiply 1 minus 2 plus 2, 0. Minus 2 times 2 minus 4 plus 5, 1. Minus 6 plus 6, 0. Minus 8 plus 8, 0. Minus 6 plus 7 is equal 1. And we obtain 0, 0, 1, 0, 0, 1. Okay, agree with me. The second operation, minus 3 times 1 minus 3 plus 3, 0. Minus 3 times 2 minus 6 plus 10, 4, 0, 0, 4. 0, 0, 4, 0, 0, 4. second step. In the second row, the second element is not equal 0, and we can put this. We can consider this element as leading element, and the second step, we can transform the element which lies below this element into 0, and then we can apply the following operation. R3 we put equal R3 plus minus 4 times R2. We rewrite first two rows, 1, 2, 3, 4, 3, 1, 1, minus 4 times 1 plus 4 is equal to 0. 0, 0, 0. We obtain the reduced row echelon form. Reduced row echelon form. And we can pass to the part 2 of our solution. We obtain reduced echelon form, and after them we try to obtain solution form for this matrix. We can consider the first column, which column contains the we have the following leading element. Which leading element lies in the first and second column. We have two elements, and we have two non-zero rows. And our goal to transform the matrix which contain two first columns and two rows, this matrix, into identical matrix. And we can apply the elementary operation of the first type. But we apply this operation in the inverse order. If the first part we subtract previous rows from subsequent row. In this case, we apply in inverse order. We can subtract the second rows in the first rows, and our aim to get in this place 0. What the operation we can apply to put to get in this place 0? We can transform the second rows R2 plus R2 times minus 2. Minus 2 plus 2 is 0. We can multiply this element, which is equal 1, on this element with opposite sign. Minus 2 R2. And after them, one, 0, 1. Easy to see this matrix is identical, and we obtain solution form of this matrix. After that, we can write the solution in the ordinary form. easy to see that the first two columns corresponds to the first unknown x1 and x2. This element are coefficients of unknowns x1, x2, and this column considers the coefficients of unknowns x3, x4. And the first equation has the following form: x1 plus 3 times x3 plus 4 times x4 is equal 0. But we want to express these expressions by this x3 and x4. And we can rewrite the first equation in the following form. We shifted this expression into right side and changed the sign before this coefficient, and we obtain x1 is equal minus 3x4 minus 4x4 plus 1. I rewrite the equation x1 plus x plus 3x3 plus 4x4 is equal 1 in this following form. I transform this expression plus x3 plus x4 into right side of this expression and change the sign. And the second expression, the second equation, we can rewrite in the following form: x2 is equal 1, and we obtain the solution in this following form. We also can rewrite this solution if we introduce two parameters, u and v, and we can use the parametric form. We can express the variable as dependent and independent in terms of some parameters. We can introduce two parameters, for example, u and v, and put this variable x4, and put the x4 equal first of these parameters, for example, u, and x4 let is equal v, u and v. x2 is equal 1, and x1 is equal minus 3 times u minus 4 times v plus 1. And we obtain the solution of this linear system in the parametric form. Using geometrical language, this form can be interpreted in the following way. U and v, we can consider u and v as coordinates of some plane. The general approach in mathematics mean that real number is a point of some real straight line. We can identify the point of distinguished straight line with real numbers. We fixed some point and we identify this point with 0, and after them we also distinguish some other other point and identify this point with 1. After them we fixed the identification between real numbers and point of this fixed real number. If we have two coordinate axes, we can identify the pair real numbers with point of this coordinate plane. And if we have two parameters, u and v, these parameters can be identified with point of this fixed coordinate plane. U, v. On geometrical language, these coordinates x1, x2, x3, x4 can be identified with coordinates of the plane in 4-dimensional space, or some 4-dimensional space. You can now imagine such a many-dimensional space, but common mathematical approach can be say us that we can do it, and we have some some 4-dimensional space. And these formulas define some embedding this plane in the 4-dimensional space. These formulas define such embedding. Yeah. Question?
Could you please once again explain how you draw that picture? How did you transform it?
I repeat. I'm not sure that I understand the question. The picture, yeah. Yes. I repeat our picture. In this picture, I try to draw the 4-dimensional space. It's enough hard for me and for us. Easy draw 3-dimensional space, and I draw this coordinate system, reference system, on the plane. But I imagine 3-dimensional space. We have perpendicular axes, x1, x2, and x3, and I imagine that this perpendicular axis. After them, I try to draw 4-dimensional space on the plane, and I draw one more perpendicular axis, x4, which perpendicular each of these axes. I try to imagine such perpendicular axis, x.
And the answer yes is that four-dimensional is 1 equal minus 3.
Yeah, I need four-dimensional space if I want to imagine the solution by geometrical way. I try use some geometrical language for interpretation of this solution. I try to interpret the solution in the geometrical language, and I try to correspond each solution of this linear system some points in imagined four-dimensional space. My solution is four tuples of numbers, and if I have 2 or 3 pair of triple of numbers, I can correspond to pair of numbers, the point in the plane, and corresponds to the triple of numbers, the point in the three-dimensional space. But now I have four numbers, and I try to correspond these 4 numbers, the point in imagined four-dimensional space. And on this way, the parameters u and v can be interpreted as one point. 2 numbers I can interpret as the point in the plane, in the some fixed plane. And this presentation of solution corresponds the embedding of this plane in the four-dimensional space. This formula defines such embedding. I embed the plane in four-dimensional space. No, this plane is this very approximate draw. It's arbitrary plane, but this plane, yes, this mapping which define if I, for example, let's consider the point M0, which has coordinate 1, 1. I substitute these values in these formulas and obtain this mapping, let's denote this mapping by F. And F maps this point in the point with coordinates. I substitute 1, 1 in this formula and obtain -7 + 1 -6, x1 -6, x2 1, x3 1, x4 1. And this point I can x1 -6, x2 1, x3 1, x4 1, and I obtain some point f m0 in this imagined space. After them, I fix other point and maps this point and some points of our four-dimensional space. And I can imagine this image of the plane as a plane in four-dimensional space. I can describe some vectors which lies in this plane. How to describe this solution? How to describe this geometrical object which corresponds to this solution? First of all, let's imagine that right side is equal 0. First of all, let me consider the corresponding homogeneous linear system. But in this case, the right side of this linear system is equal 0. And in this case, this constant term are equal 0. And in this case, the general solution has the following form. x1 is equal minus 3x3 minus 4x4, x2 is equal 0, And in the parametric form, we obtain the following expression. In this expression, I can put the constant number equal 0. And I obtain the parametric form this equation. x1 is equal minus 3u minus 4v. x2 is equal 0, x3 u in the geometrical language, we obtain the plane which passes through origin of this coordinate system. This plane is parallel to the initial plane which corresponds to the solution to in homogeneous system. This two parallel plane. This plane is subspace, vector subspace of our four-dimensional space, and we can describe this vector subspace as a subset of linear combination of some basic vectors which generate this subspace. How to describe this basis vectors? I try present this element of this vector space as a linear combination of some vectors. I can choose the basis in this initial plane, which has coordinate axes u and v. In this plane, I have two basis vectors, this one and this one. This vector has coordinate 1, 0, and this vector has coordinate 1, 2. Let this vector E1 and this vector E2. I have two coordinate vectors. This coordinate vector corresponds the images of these vectors, the sum vectors which lies in this plane. And our maps is embedding. And this this basis vectors maps to the basis vectors in the image. And let's describe these images. Fe1. Fe1 has the following coordinates. I substitute in this formula u is equal 1 and v is equal 0. And I obtain the following coordinate. x3 is equal 1, x4 is equal 0, x2 is equal 0, and x1 is equal minus 3. And I obtain the following first basis vector, minus 3, 0, 1, 0. This vector is the image of these vectors in this in the image of this coordinate plane. The second vector, E2, is this vector has a coordinates 0, 1. And I substitute these values in this formula, and I obtain the following coordinate. X1 is equal minus 4, x2 is equal 0, x3 0, x4 1. And I obtain the coordinates of the second basis vector in our plane. This vector has the coordinates minus 4, 0, 0, 1. Do you understand? Yeah? And arbitrary vectors has the coordinate uv. What does it mean that this arbitrary vector has this coordinate uv? This means that this vector x has the form u e1 plus v e2. And the image on this vector in the four-dimensional space has the following coordinates. F transform my mapping F transform this vector x in the vector u f e1 plus v f e2. And we obtain, and we obtain the following answer. This formula can be rewritten in the following. Can be rewritten in the following form. The first vector f e1 minus 3, 0, 1, 0 times u plus v minus 4, 0, 0, 1. And after simple transformation, we can see that we obtain this formula. We present our solution as a linear combination, some basis vectors, which are the images of distinguished basis vector in the coordinate plane. We obtain some presentation with some vectors. But in our solution, we have constant term, the point which has coordinate x1, x2, x3, x4, x3u, x4v, x2 1, and x1 minus 3u minus 4v plus 1. The general solution of the initial non-homogeneous system. If I put the values of independent variables equal 0, I obtain some point of our plane. And this point, M1, has a coordinate 1, 1, 0, 0. The some distinguished point M1. This point is the image of point of origin of initial coordinate plane. My map maps this plane in the some plane of the four-dimensional space, and this map maps the origin of the system some distinguished point of this plane, and this point has a coordinate 1, 1, 0, 0. And my general solution can be present in the following form: the linear combination of the basis vectors and coordinates of this distinguished point, plus and we obtain the parametric form of this plane. We have in the course of analytic geometry the parametric form of the straight line in the three-dimensional space. I recall this following form: x, y, z, m, and p would be the coordinate of the vector direction of the straight line, times t plus x, 0, y, 0, z, 0, the coordinate of some point of this straight line. This form is the same. We have one directed vector. In this case, we have two two basis vectors. These vectors of direction of straight line is the basis vectors of the straight line. In this case, we have two vectors. In this case, we have coordinates of some distinguished point on the straight line. In this case, the same way we have also the coordinate of the some distinguished point in the plane. And we can see that such parametric form is enough general for arbitrary hyperplane in the many-dimensional space. And any solution of arbitrary linear system can be interpreted as some hyperplane in the many-dimensional space, and can be presented in the same form as the equation of the straight line. Any question, maybe? This language is very useful, and we will use further this language and this geometrical interpretation can be helped to better understand the sense of these algebraic formulas. Okay, and using this language, we first of all solve the second equation. After them, we try to interpret it in geometrical language, the solution of this linear system. And let's try to solve the second linear system. We have homogeneous linear system. The constant term I equal 0. And in this case, augmented matrix and coefficient matrix essentially coincide. And I can write on the coefficient matrix. Coefficient matrix has the following form: 2 minus 1 minus 1, 2 minus, oh, I'm sorry, 1, 1. 1 minus 1, 2, 1, 0, minus 3 minus 3, 1, 5, 6, 0, 0, 0. 0, 0, 0. Our goal to obtain the reduced echelon form of this matrix, and first condition, first property of row echelon form is a basic leading element must be equal 1, and enough convenient change place first, for example, third rows, and after them we obtain the first in the first place. Excuse me, I have no time. Okay. And the first operation, we change places the first and third rows. I can change first and second rows and change the sign. It's equivalent way to solve. But after this transformation, I obtain the following matrix. I can now write the constant term is equal 0, and after transformation is not changed. -1, -1, 2, -3, 4, 2, 2, -1, 0, 1. And second transformation, I must put R2 is equal R2 plus R1, R3 is equal R3 plus -2 times R1. The first row is not changed. Second row 0, 0, 3 minus 6, 11 minus 6, 11 0, 0 minus 6 minus 6 minus 12 plus 1 minus 11, and last step I can add to third rows second, and after then I obtain and last step I try to obtain the reduced echelon form, and I divide the second rows on the leading element in the second rows on 3. R2 I put is equal the ratio 1, 3 R2. The second rows is not changed. 1, 1, 1 minus 3, 6. The second rows 0, 0, 1 minus 2. The ratio 11, 3. And I obtain the reduced echelon form. I mark the column 0 rows. I mark the column which contains leading element. I have such first and third columns. I mark the leading element 1, 1, and I have 1 and third column. And my goal transform the matrix which contain these two columns into identical matrix. And the operation I put R1 is equal R1 plus minus R1 is equal R1 plus minus 1 times R2. After this, transformation, I obtain the solution form on this matrix. I will write 0 rows. The second row is equal 0, 0, 1, minus 2, the ratio 11, 3, 1, 1, 0, 1, 1, 0, plus 2 minus 3 is equal minus 1. The ratio 18, 3 minus 11, 3 is equal to the ratio 7, 3. 7, 3. And I obtain the solution form. I obtain the solution form. First and third columns forms the identical matrix. And this column corresponds to dependent variables x1 and x3. The variables x2, x4, and x5 are independent variables. And we can write, in this case, the general solution, namely x1, x3 is equal. x1 is equal, I transform in to right side the independent term, and I obtain the following expression: minus x2 plus x4 minus ratio 7, 3, x5, x3 is equal to x4 plus ratio 11, 3, x5. And we obtain the general solution of this linear system. And let's present the solution in the parametric form. x1, x2, x3, x4, and x5. I have 3 parameters. x2 is equal u, x4 is equal v, x5 is equal w. x1 is equal minus u plus v minus 7, 3, x5. x3 is equal to v plus the ratio 11, 3, x, the ratio 11, 3, w. We obtain the parametric form. Let's interpret this solution using geometrical language. We have 3 independent variables. This means that we have 3-dimensional hyperspace, but we have the solution, we have 5 unknowns in our equation. The solution is a 5-tuple. 5-tuple is a point in the 5-dimensional space. In this case, we have 5-dimensional space. And in this 5-dimensional space, this formula defines the embedding 3-dimensional hyperspace. We have the same presentation as the previous example. We have 5 unknowns and 3 independent unknowns. In this case, we can say that the dimension of the vector space V of vector space, of general vector space, which help us to interpret the solution as a point in this vector space. This vector space has a dimension which is equal 5, and our solutions form 3-dimensional space which embed in this 5-dimensional space. And difference between space of the difference between dimension of vector space and the space of our solution, 5 minus 3 is equal to 2. This difference is called codimension of this hyperspace, and we have hyperplane which has the codimension 2, and this hyperplane embed in the 5-dimensional space. And the general form of such solution is the same as in the previous case, and the same as the case of equation of straight line, which embedded in 3-dimensional space. We have the general form for the various type hyperplane in many-dimensional space. If the two hyperplanes have the same codimension, the form presentation in the equation of such geometrical object is the same. We have some parameters. Oh, I'm sorry. W in this case. We have, easy to see that we have 3 independent parameters, U, V, and W, and we can present this general solution in the following form, как linear combination of the two basis vectors, x1, x2, x3, x4 is equal. I put u is equal 1 and v is equal 0, and I obtain the first vector minus 1, 1, 0, 0, 0 times u. The second vectors can be obtained if we put the u is equal 0 and w is equal 0. V is equal 1. V 1, 0, 2, 0, V. And last basis vector we obtain if we put the first two parameters I equal 0, U and V equal 0, and W is equal 1. And we obtain minus 7, 3, 0, ratio 11, 3, 1. Times W. And we present our solution, our three-dimensional space, as a linear combination of the three basis vectors, which has the following coordinates. First has coordinates minus 1, 1, 0, 0, 0. Second basis vector has the coordinates 1, 0, 2, 0. And the third basis vector has the coordinates the ratio minus 7, 3, 0, 0, ratio 11, 3, and less coordinates is equal 1. And the same way I can interpret, I can imagine this solution as some hyperplane, three-dimensional hyperplane, which embedded into five-dimensional space. And these vectors are the basis vectors of this space of solutions. Any question? Maybe.
Excuse me.
Yes.
Everything is clear for the examples, but would you please send us the notes, the lecture and seminar notes?
What, repeat please, what?
Would you send us the lecture and seminar notes?
Yeah, I sent. Okay.
Everything is clear.
Yes, this example is clear for you? Yes. Yes. Yeah. These parameters. Yes, this coefficient, this coordinates of the basis vectors, and I times on the arbitrary parameters. I present any solution as a linear combination of this basis solution, and I can put these parameters equal arbitrary real numbers, and this simple and very simple form to present all solutions. I have infinitely many solutions, but this infinitely many solutions can be expressed as an arbitrary combination of finite numbers basis solution, and easy to imagine present this infinitely many solution as in the terms of finite numbers of solution, and very simple and convenient form presentation, the simple idea. I have some distinguished solution, and this minimal numbers of such solution, I cannot express any of the solution in terms of other solution, is a definition of the basis. But I can any solution in the as a linear combination of this solution is a very efficient presentation for solution. Yeah. And I can imagine geometrically all the solution. I can imagine the many-dimensional space, but it's very hard for me, but I try to imagine, and I can imagine three linear independent vectors, and these three linear independent vectors generates the all solution, generate as a infinitely many linear combinations of the solution. I can imagine this picture, and I have some geometrical language for description of the solution. Okay. Сколько времени уже? Okay. Yes. And after this, the main aim of our seminar to explain the geometrical language for description of solution of linear system. And we have more time, and we can try to solve a more hard problem, and consider the case when the linear system has one or more parameters, and we have infinitely many systems which can be described as one linear system with parameters. For example, let's consider the problem 3. The coefficient and constant term contain some parameter a. It means that we have infinitely many linear systems. For every value of parameter a, we have separate linear system. And our goal to study this infinite set of linear system, and for every value of parameter describe the solution. To study for every value of parameter, we can ask, have this separate linear system, has this separate linear system solution or not? If this linear system has solution, how many solutions has this linear system? One or more, infinitely many maybe. And first of all, let's rewrite this linear system using matrix formalism. The first column 1, 3, 4, 2, minus 1, 1, minus 3, 5, and we have parameter a square, I'm sorry, 4, 1, a square minus 14, 1, and constant term 4, 2, r plus 2. Okay, and in this case, we can some way we can solve this linear system. We will use Gaussian elimination method, and we have enough evident transformation. Let's put easy to see that this term can be considered as a leading term, and after the first transformation R2, we can put R2 plus minus 3 R1, R3 is equal R3 plus minus 4 R1, and we write first row multiply first row minus by -3 and adding to second rows, we obtain 0, -6 minus 1 minus 7, 9 plus 5, 14, minus 12 plus 2 minus 10, minus 4 plus 4, 0, minus 4 plus 1 minus 7, plus plus 12 is equal to r square minus minus 2. And this minus 16 check please my calculation. Minus yes, okay, and last step, R3, put R3 is equal R3 plus minus R2, and we obtain 1, 2, minus 3, 4, 1, minus 7, easy to obtain reduced echelon form. 1, 2, minus 3, 4, 1, 0, 1, 2, minus the ratio minus 10, 7. And the last term and we can investigate this linear system. What can we say about solution of this linear system? Easy to see that if a square minus 6 is not equal 0, this system has a unique solution. Easy to see. If this term is not equal to 0, we have unique solution. We can transform this matrix into identical matrix, and after them we can express these variables in terms of constant members, unique way. But if this term is equal 0, we have two various cases. If a square is equal 16, it does mean a is equal 4, a is equal minus 4. And we have essentially various cases. In first cases, the constant term is also equal 0, and we obtain that the third equation, the third rows is equal 0. All terms in these rows are equal 0. And in this case, our system has infinitely many solutions, and we can describe the solution. In this case, this term is equal 0, but this is equal minus 8. And in this case, the system has no solution. Let's describe these cases. First, a is equal minus 4. System has no solutions. First case. Second case. A is equal 4. This system, in the system, the third rows became is equal 0, and in this case we obtain the following linear system: 1, 2, minus 3, 0, 1, 2, 4, the ratio minus 10, 7. And we can transform this reduced echelon form into solution form. If we put R1 is equal R1 plus minus 2R2, and we obtain minus 4 minus 3 minus minus 7 minus 4 and we obtain the solution x1 is equal 7 x3 plus the ratio 48 7, x2 is equal minus x3 minus the ratio 10 7. In the second case, when I is equal 4. And last case, R square is not 16. In this case, we can rewrite our system in the following form. And in this case, we obtain that our system has a unique solution. We can put R2 is equal R2 plus minus 2 R3, R1 is equal R1 plus 7 R3, and we obtain the following final form. X1 is equal in this case. We obtain that our system has unique solution, which defined by the following formulas. Any question? Repeat quickly. Our initial system has the following form. I consider this term first of all. This term is equal r squared minus 16. If this term is not equal 0, our system has unique solution. If this term is equal 0, we have two various cases. R squared is equal 0, which is equivalent, a is equal 4 and a is equal minus 4. In this case, when I is equal minus 4, this term is equal 0, or this term is equal minus 8. And we have the equation left side is equal 0, right side is not equal 0. In this case, system has no solution. Second case, this term 0, this term 0. And in this case, the third row is equal 0. And in this case, we have infinitely many solutions, and our matrix has the following form. We are using Gauss elimination method. This reduced echelon form we transform into solution form, and obtain the following solution. In this case, we have infinitely many solutions, and the solution described by the following formula. And the second case, when a square is not equal 16, and in this case we have unique solution. I rewrite the second equation. I divided left and right side on this case. I transform leading term into unit, and this